In this illustration, we'll study about extraneous charges at the dielectric boundary. Here we are given that a parallel plate capacitor is filled up with two dielectric layers 1 and 2 with thicknesses d1 and d2 and dielectric constants k1 and k2 and with resistivities ρ1 and ρ2. And a voltage V is applied to the capacitor with electric field directed from 1 and 2. And we are going to find the surface charge density of charges appearing at the boundary of dielectrics. Now in this situation, if we draw the capacitor for better clarity, here this is the capacitor. And there are two dielectrics filled in it. They are having width d1 and d2, dielectric constants k1 and k2 and with resistivities ρ1 and ρ2. It is connected across a battery of EMF V. Now in this situation, we know as the dielectrics are having resistivity, the capacitor will have a leakage current, for which we can directly first calculate the resistance between plates, which can be given by the series combination of the resistance of the two dielectrics. If we consider here the plate area is equals to A, then we can write this resistance as ρ1 d1 by A plus ρ2 d2 by A. As we are having resistance, then a constant leakage current will flow as a constant potential difference V is applied here. So we can calculate the value of leakage current in capacitor, which can be given as V by R. So on substituting the value, we can see it as VA by ρ1 d1 plus ρ2 d2. This is the current flowing between the two plates. Now here, if we wish to find out the surface charge density of charges appearing on this boundary, here we can split this capacitor in two capacitors considered in series. Here you can see, if I consider two capacitors connected in series, this is C1, this is C2, and they are connected across a battery of voltage V. Then also here we can see a current I is constantly flowing through the system. But in this particular case, on the two plates connected with the capacitor, the charges will not be same. So here we can write down the value of charges appearing on these capacitors as plus Q1 minus Q1 and plus Q2 minus Q2. Here we can find out the charges on plates X and Y are. Here we can consider this plate as X and this plate as Y. So charge on plate X, we can write it as minus Q1 and the value is C1 multiplied by the potential difference across this capacitor. So value of C1 we can write as K1 epsilon naught A by D1 multiplied by the potential difference across this will be IR, that can be written as VA by ρ1 d1 plus ρ2 d2 multiplied by the resistance of this leaky capacitor. This is ρ1 d1 by A. So in this situation here we can see this d1 and A gets cancelled out and the value of Q1 we are getting is negative of this ρ1 k1 epsilon naught VA divided by ρ1 d1 plus ρ2 d2. Similarly, charge on capacitor C2 on plate Y we can write as Q2 and this is equals to C2V. So C2 is K2 epsilon naught A by D2 multiplied by the potential difference across this capacitor, which is again written as IR. Here I is VA upon ρ1 d1 plus ρ2 d2 multiplied by its resistance, which is ρ2 d2 by A. So here d2 by A gets cancelled out and simplifying this will give us the value of Q2, and the value of Q2 here we can see it is ρ2 k2 epsilon naught VA divided by ρ1 d1 plus ρ2 d2. So we wish to calculate the charge density on this boundary, we can again combine the two, and the total charge on this boundary can be written as Q2 minus Q1. So surface density on boundary can be written as Q2 minus Q1 divided by the surface area. So if we substitute the values of Q2 and Q1, again A gets cancelled out, and the result we are getting is epsilon naught V multiplied by rho 2 K2 minus rho 1 K1 divided by rho 1 D1 plus rho 2 D2. This is the final result of this problem, which is considered as the extraneous charge at the boundary of the two dielectrics in this situation.